So question number one is a factoring question. A couple of people have come up with the right answer. I'm just going to review the method of doing that, and then we'll go on with some other questions. Remember, when you're factoring a trinomial, three terms, the first thing you want to do is look if there is a common factor. Is there a number that goes through all of them? And there isn't one here. And since this number is, this x squared is starting with a number, there's a leading coefficient of 15. What we're going to use is what we call the AC method. We're going to multiply the 15 times the -8, which will give us -120. And what we're looking for is two numbers that will multiply to a -120, which means, of course, one is going to be positive and one is going to be negative. And when we combine them, which really means when we subtract them, we're going to get 14. And this is something that we have to use our calculators. It's going to be a help. Let's see, what things multiply to 120? Well, certainly 2 times 60. But that doesn't give us, when we subtract, it doesn't give us 14. So we can type 3 times 40. Which is also not going to be good because 40 minus 3 is 37. We're still too far apart. I'm going to keep going. What's the next thing that multiplies? 40 times 30. Still no good. 30 times 40 is 30 minus 40 is 24. I'm going. Let's see. 5. 5 goes into 120. If we do 120 divided by 5, we get 24. We're getting closer. 24 minus 5 is 19. It's not 14. So let's try 6. 6 times 20 certainly works because 6 times 20 is 120. And when I do the 20 minus 6, I get the 14. And we're going to have to make the 20 the positive one and the 6 the negative one, because this is a positive 14, so we need our larger number to be the positive one. Do you notice how I went through, I just took numbers, started with this simplest set divide. 2 goes into 120, 3 goes into 1, until I came up with an answer. So I'm going to rewrite this trinomial into a 4-termed expression. It's going to be 15x squared minus 6x plus 20x minus 8. In other words, I rewrote the 14x as -6x plus 20. And it doesn't matter what order you put this in. You could have put the 20x first and the -6x second. Just be careful with the signs. Okay, then we're going to look. In this, we're going to do grouping. In the first group of 15x squared minus 6x, there's a common factor of 3x. If I divide 3x into 15x, I'll get 5x. If I divide the 3x into the -6x, I get -2. In my second group, which starts with a plus, so I'm going to have a plus, I have a common factor of 4. 4 goes into both 20 and into 8. So 4 into 20 gives you 5x, and 4 into -8 gives you -2. And we see that we have now this common binomial factor of 5x minus 2. So that goes into my first parentheses. And my second parentheses becomes the 3x plus 4, the two numbers that are on the outside. And it doesn't matter which one comes first. When you factor, the order of the two factors does not make a difference. What makes a difference is the signs. You have to make sure you have the right signs in the right order. And I think those were the answers that I had been sent by our on the chat. Thank you very much. Okay, so let's now go on to question number 2, which happens to be a multiplication. You're multiplying, remember, chapter 4 is all about polynomials, adding, subtracting, multiplying, dividing, not dividing, factoring, adding, subtracting, multiplying, and factoring. So let's see, this is a multiplication. We're multiplying two binomials. Remember, if you would have a binomial with a exponent of 2 on the outside, a square, you have to write it twice and again do it this way. You have to use FOIL. First, 8a times 9a is 72a squared. Outer, 8a times 7b is 56ab. Inner, negative 12b times 9a. So 12 times 9 is 108. So that becomes negative 108 AB. And finally, negative 12b times 7b. So 12 times 7 is 84. So that's negative 84b squared. Remember, these are large numbers, but you're allowed to use your calculator, certainly for these multiplications. Now, I'm going to combine the like terms. So the first, there's nothing to combine with the 72a squared, so we leave that 72a squared. The positive 56 and the negative 108 can be combined to negative 52ab. Be careful with your signs. A positive, this is the larger one, so you get a negative answer, and then negative 84b squared. And that would be your answer. This was the answer for number 1. Here's the answer for number 2. Number 3 is what we call a quadratic equation. In a quadratic equation, we have what we call a second degree, an exponent of 2 in our equation. And when we solve the quadratic equation, we want all the terms on one side equaling 0 on the other side. If we're using either the factoring method or the formula method, in this case, I'm going to we haven't talked about quadratic equations yet in chapter 4. So this is just a simple factoring example. This is an easier factoring because the leading coefficient here is just 1. It's just a plain x squared. So I can break that up into x and x. And 48, I'm looking for two numbers that multiply to 48. Obviously, one's going to be positive, one's going to be negative because it's a negative 48. And when we subtract those two numbers, we want to come up with 2. And I think it's fairly obvious that the number should be 8 and 6. 6 times 8 is 48. 8 minus 6 is 2. And we're going to make the 8 the negative because this is a negative sign in the middle term makes the larger number negative and the smaller number, the 6, is positive. I then set each of these equal to 0. Remember, you're not finished yet. You only go further. Notice here we didn't do that. This was just a factoring. It was just breaking it up. This is an equation. We have to solve it. We'll know it's an equation, first of all, by the instructions, and also the fact that it'll have an equal sign in it. We separate each of these into two smaller equations, sending them each equal to 0. So in the first one, I'll get x equal -6. And here I'll add 8, and I'll get x equals +8. When you're solving a quadratic equation, you expect to get two answers. So those are how these three questions, which came out off of different final exams. These are all regular final exam questions. Excuse me. Okay, so I think what we're going to do now is to go back to Chapter 8, the last chapter that we're covering for this term. And I'm going to give you a couple of questions to review, to try as a review of what we had done the other day as when we started this chapter. And then we'll continue from there on. Keep in mind that our final exam is coming up on us. It's not this week, but it's a week from Thursday. And if you have a conflict, and I saw one person did email me about a conflict, and I did not reply, but I'll check it out. You have to let me know. I would prefer everybody taking the final exam at the same time, because then on Thursday from 9 to 11, I will be at my computer and constantly be checking my emails if anybody runs into problems. Some of you have already run into problems when you try doing the practice midterm or the midterm itself or the practice final. Sometimes the computer just shuts off on you. Now, the only thing I can do is restart you. I can't get you back to where you were. I can restart you on so that you have another full 2 hours, etc. So I can do that, but that has to be that I should be online and know that you are having this problem. If you're going to have to do it at a different time, you have to have a good reason, number one. But number two, I might not be online at that particular moment when you're taking it. So keep that in mind. Also keep in mind that there is tutoring. I sent out a flyer with all sorts of times for tutoring for the Math 136 final. This schedule is specifically with Patrice. She's going to be there Monday today from 12 to 2 and Tuesday from 1 to 4. That's in room L00 in the Science and Technology building. So if you want to have any in-person tutoring, which is always a very big help, try to come at those times. Patrice is an excellent tutor. You've seen her in action when she took over. Okay, so let's go back to a couple of the questions that we had learned or done. From chapter 8. Okay, first of all, what if I gave you a question that looks like this? And I asked you to simplify it. It's x squared, x to the negative 2, y to the third, z to the fourth to the negative 3 power, times x, y to the fourth, z to the 0 power. I'm going to give you a minute to try that, see if you remember what we did with that. While you're doing that, I will take attendance. I'll just do it from the participants. Okay, Alvaro, I see you're here. Emma. Harley. Kayla. Piano. Ariana. Okay, and Patrice. So, okay, let's work on this together because it looks pretty complicated. So the first thing, if you recall what I said, is that if you have an expression with exponents and you have exponents on the outside, you're going to distribute the exponent on the outside to each of the letters and numbers that are here. So that, and when you have two exponents on an expression, what you're doing is you're multiplying the exponents. Remember, even if something doesn't have an exponent on it, if it's just written plain like x, that really means it has an exponent. The exponent is understood to be 1. Okay, so here what we're going to do is the x to the -2 to the -3. So we'll multiply the -2 times the -3, and that'll give us x to the 6. The y will become y to the -9. And the z will be to the -12, because I'm multiplying each of the exponents by the -3. Over here, I have an expression that's written to the 0 exponent. And if you recall what we said, when you have a 0 exponent, you are not going to have, it's going to be, doesn't matter what it is, it always ends up being equal to 1. So this whole thing is just equal to 1. So we could really just sort of ignore that. So anything to the 0 exponent is 1. What do we do when now we have to go further, because we don't want to leave our answers with negative exponents. When we have negative exponents, it really means that we're going to have a fraction. So the next thing I do is I draw my fraction line. This really, it's you should understand that anything that isn't a fraction is really can be written as a fraction over 1. So this whole thing is over 1. We're now going to move things around so that anything with a positive exponent will stay where it is. Anything with a negative exponent will get moved. That means if it's in the numerator, it'll go to a denominator. If it's in the denominator, it'll go to the numerator. It turns out we only have a numerator here, so everything, if we're going to have negative exponents, they're going to go down. Well, this x to the 6 has a positive exponent, it stays on top. But the y to the -9 comes to the denominator, and the z to the 12th also. Notice when we move them, we make their exponents positive. This is times 1. I can't simplify this any further, so this would be my answer. So remember, when you have negative exponents, they mean that you're taking the reciprocal. We also talked about having fractional exponents. So if I were to ask you, can I erase this now? No projections, so I'm erasing it. If I give you something that looks like this, 81 to the 1/2 power, remember what a fractional exponent means. It means you're not multiplying by it 1/2. It means you're doing a radical where the denominator of the fraction gives you the what we call the index of the radical. A 1/2 means just a regular square root. This is the same as asking what is the square root of 81. And of course we know what the square root of 81 is. It's 9. So fractional exponents are no different than what we did in chapter 7 when we talked about radicals. We know how to deal with radicals. We know how to deal with fractional exponents. If I give you something like this, 125 to the 1/6 squared, let's say, ask you to do that. So the first thing I've got to do, I have 2 exponents here. I have to use my rule of exponents to get rid of, so that I'm dealing with just a single exponent. I want to deal with 2 exponents. And I know when I have something with an exponent raised to a second exponent, it means that you're going to multiply the 2 exponents. So I'm going to multiply the 1/6 times 2. Now remember, 2 really means 2 over 1. So that gives you 2 over 6. which reduces to 1/3. So this question really is asking us, what is 125 to the 1/3 exponent? Now, if you want, you could stick it into your calculator. You put in the 125, you press your exponent button. In most calculators, put in the 125. In most calculators, the exponent button looks like a little arrow pointing up, or a caret. As a matter of fact, I'm sure some of you have used this as when you're typing and you want to type an exponent, that you use this little symbol. That's the exponent symbol. So you're going to put that in, and then since this is a fraction, you're going to do a parentheses, 1 divided by 3, and you're going to close the parentheses. You can't just do 1 divided by 3 without the parentheses, because the calculator will think that the only exponent is the 1. You have to put whatever you want to be. If it's not a single number, if there's more than one number in your exponent, you have to put it in a parentheses. Now, if you do this, you'll see that what you get is 5. If you do it on your calculator. Why is that? Because 125 to the 1/3 exponent is equivalent to the radical of 125, where the index, the little number over here, is 3. That's because this is a 1/3. Now, what does this mean? This is read the third root or cube root of 125. The index tells you how many times you have to multiply the number to get the number inside. So we're looking for a number that when you multiply it 3 times will give us 125. And you see 5 work. 5 times 5 is 25, and 25 times 5 is 125. So again, your answer is 5. These are not so difficult also as multiple choices, because then they give you, you're starting with just 4 answers, and you should be able to tell which is the correct answer. So that's what we had reviewed in terms of working with exponents and the different kinds of exponents: whole numbers, 0, negative numbers, and even fractions. Any of those can be exponents, and you can stick it into your calculator, and your calculator understands these type of exponents. So another thing that then we talked about how to solve something called an exponential equation. So let's say I gave you something that looks like this. Let's say I gave you this equation. Three to the 2x minus 4 equals 9. Okay, this is something called an exponential equation. Notice where the variable is. The variable is in the exponent. We know what the base is. The base is 3. That's the number that has the exponent. And the exponent is the 2x minus 4. And one of the ways we try to solve an exponential equation is by getting both sides of the equation written in terms of the same base. Wow, you're way ahead of me, Kayla. Okay, now what is the base we're going to use? Since the 3, this is base 3. In other words, we're going to try and get the 9 to be written in base 3 as well. And we can do that because 3 times 3 is 9. We're not talking about what happens if you can't do it. We're just dealing now, right, with questions where you can do this. So we rewrite this as 3 to the 2x minus 4. We leave that alone. But the 9 we write as 3 squared. And now that both the bases are the same, we can solve it by setting the 2 equal exponents together. In other words, the 2x minus 4 has to equal 2. And then you get an equation. That's not a very difficult equation to solve. You'll put, this is a regular equation. In other words, you forget about the bases because they're both the same. You just work with the exponents. So this gives you 2x equals 6. And if you divide by 2, that'll give you that the x would equal 3. And it makes sense because 2 times 3 is 6 minus 4. That makes this whole thing equal to 2, and 3 to the 2 is 9. It does work. So that's how we solve an exponential equation. Let me give you one to try on your own. And Kayla, I'm going to give you extra credit for doing that. Okay, so here's an example for you to try. Two to the 5x minus 1 power equals 8. I'm going to give you a couple of minutes. They don't always come out to be whole numbers. Sometimes they come out to be fractions. Anybody have an answer for this one? Let's see if that's correct. Anybody besides Kayla? Okay, let's try it together. Again, look, try to get both numbers to the same base. Again, if you can't do it, then this method doesn't work. Sometimes the method works, sometimes it doesn't. When we can't do this method, we'll have to think of a different method, but right now, this is the only way we know how to do it. So here the base we're using is 2, so I'm going to try and get the 8 in base 2 as well. So let's think about it. 8, 2 times 2 is 4, and 4 times 2 is 8. In other words, 8 can be written as 2 to the third. So I can now write this as 2 to the 5x minus 1 equals 2 to the third. And now I can, since they're both the same base, I can only do this when they're the same base. I can set them equal. 5x minus 1 has to equal to 3. And I'll bring the 1 to the other side, which will give me 5x equals 4. And the correct answer is 4/5. Notice it can be a fraction. Yes, it can be a fraction. That was the correct answer. Who else gave me a correct answer? Emma, okay, that is correct, yes. Okay. So we're going to go on today and to talk about something that's called a logarithm. And the abbreviation for logarithm is log. So this is unless you've actually studied this topic before, this is something totally different than, this is no longer part of algebra, really. It's what we call a transcendental function. Doesn't work algebraically. What does it mean? What does a logarithm do? So let me start by explaining some of the relationships we have when we do different operations. For example, I could say that 5 plus 3 equals 8, using the operation of addition. I could have said given you the exact same information by saying 8 minus 3 equals 5. Same thing, written with a different operation. This is the operation of addition. This is the operation of subtraction. The two operations, addition and subtraction, work together. They are what we call inverse operations. If I add two numbers, I'll get an answer. If I take the answer and subtract one of the numbers, I'll get the other. The inverse operation sort of undoes what the original operation did. It's called the inverse operation. Where else do we have inverse operations? Well, what about multiplication? 5 times 3 is 15. We get the same thing by doing 15 divided by 3. It'll give us 5, the same numbers. And sometimes we use a division sign, and sometimes we use a fraction sign. But division is the inverse operation of multiplication. It undoes the process of multiplication. If you take a number, the answer that you get for multiplication, and divide it by one of the numbers, you get one of your original numbers. So these are examples of what are inverse operations. They sort of undo what the other one does. Or try to think of it this way. In this question, you take the answer and try to go back to your question. My answer was 8. If I subtract 5, what is my original number that I was adding? Obviously 3, or if I take away the 3, my same thing with here. 5 times 3 is 15. If I start with my answer 15 and divide it by the 3, it gives me back to my 5. So it sort of takes the answer and gives you back your question. That's what the inverse of an operation does. We're going to see when it comes to exponentials that this thing called a log is really the inverse of exponents. And when we have an expression in log, what we call logarithmic form or log form, it's really telling us the same thing that we learned from exponentials, except starting from a different perspective. Just like 8 minus 3 gives us 5, is giving us the same information that 5 plus 3 equals 8, but from a different perspective. It's starting with one of the answers and going back to one of the questions. But the basic information that you're getting is the same in both cases. The same thing like the 5 times 3 and the 15. If you start and you do it with the division, you're starting with your answer, but you're just looking at it from a different perspective. Division is a different perspective than multiplication, but they are sister operations because basically you have to know how to do one in order to do the other. So with that explanation in mind, let me give you an example. Let's say I started out, I'm going to start with an expression in exponential form, and then I'm going to write it in logarithmic form. You're going to see it's a different format, but it's giving you the same information. Suppose I start with the information 2 to the 3rd power equals 8. This is something we know from before, because 2 times 2 times 2 gives us 8. This is exponential form. Here's logarithmic form. We write the word log. There's a subscript next to the word log, which is the base of the exponent. Next to the word log goes the final answer, and that equals 3. This is the logarithmic form of this statement. This statement is read 2 to the 3rd power equals 8. This statement is read the log base 2 of 8 equals 3. They're both giving you the same information from a different perspective. Here your answer is 8. Here you're using the 8 in your expression and your answer is 3. I think if you, instead of the word log, in your mind read exponent, the expression is going to make sense. The exponent that you put to base 2 to get the number 8 is 3. So what an logarithm is just an exponent. So what's the difference between the exponential form and the logarithmic form? In the exponential form, you're starting out knowing the base and the exponent, and you try to get the answer, which is usually not too hard. If you don't know, you could do it on your calculator, whatever. In the log form, what you're starting out with is your final answer, and you know your base. What you're looking for is the exponent. Now, what's the big thing they have to know here. You have to be able to switch from one format to the other. Just as you can switch from addition to subtraction or from multiplication to division, as long as you switch the numbers properly. The same thing, you can switch from exponential form to logarithmic form. And that's the first thing we're going to work on. We're going to take a bunch of examples and switch them from log form to exponential form and vice versa. So let's say I'm going to give you the rule. I'm going to give you the basic rule, so we can use it as a format. If we say b to the, I want to make sure I'm doing this the way I did it on the sheet. This is from the study guide sheet that I sent you. This is exponential form. This is equivalent to, it means the same thing as log base b of a equals c. This is the log form. Okay, so let's do a couple of quick examples where we have to switch from exponential to log and from log to exponential. Okay, I'm going to write something in exponential form. I'm going to give you a couple minutes to see if you can write it in logarithmic form. Let's say I write this statement: 2 to the negative 5 equals 1 over 32. Now, this is a true statement. How do I know that? Well, the negative is telling me that it's going to be a fraction. It's going to be in the denominator, because that's what a negative exponent does. It gives you the reciprocal. And 2 to the 5th is 2 multiplied 5 times. 2 times 2, 4, 8, 16, 32. So this is a true statement in exponential form. See if you can write this same statement in logarithmic form. I'm going to give you a minute. All right, I'm going to do it with you. Okay, remember, keep this as your pattern. If I want to write it in logarithmic form, here's my word log. The subscript, the number that goes here, is the base, the number that has the exponent. Well, I know what has the exponent. The base is 2, so this is going to be a subscript of 2. So generally, where the base is not hard to figure out where to put it. The question is what goes here and what goes here. So the log, remember, think log means exponent. So the log equals the exponent. The exponent is going to be the negative 5, which means this, what goes next to the word log is the 1 over 32. These two things are telling you the same exact thing. Now, if you're able to switch from log form to exponential form, then some of the questions that get asked sort of makes sense if you can take the logarithmic form and switch it to exponential form. For example, let's say I gave you this question. Log base 3 of x equals 2. And I told you, I'm going to erase this now. Okay, so this I don't notice in both exponential and logarithmic forms, there's really 3 numbers that you're dealing with. You're dealing with the base, the exponent, and the final answer. In this case, they gave us 2 of the 3 numbers. They want us to figure out the other numbers. Now, let's face it, I just taught you logs. I just taught you what the format is. If you have a lot of experience with it, you can automatically think it in your head. But most likely, this looks like Greek to you. It's not Greek, it's really English, but I don't know where the word logarithm came from, but it's not a Greek word. Trigonometry came from the Greeks. I don't know where logarithms came from. But I would suggest is keep in mind how to switch from the log form to the exponential form. Now let's remember, log form, the subscript 3 is going to be the number with that is the base. The number it's equal to is the number that's going to be the exponent. So the exponent is a number that's always on the other side of the equal sign of the log. So the exponent is 2, and that's going to equal x. Notice how I've gone from log form back to exponential form. But now it's an easy question to answer. X is 3 squared. Well, 3 squared is 3 times 3. That must mean my x is 9. I would say almost half the questions on logarithms can be solved if you put it from logarithmic form back to its exponential form, where it'll look more familiar and you'll be able to answer the question. Let's say I gave you this example. Log base 2. Let's say I ask you that question. See if you can answer that. Okay, let's see if we can do this. Again, it looks strange in logarithmic form, so we're going to change it to the exponential form. Our base is the subscript. That's always our base. Our exponent is the number on the other side of the equal sign, which in this case we don't know, it's x. That equals 16. So my logarithmic equation becomes the exponential equation 2 to the x equals 16. Well, we just learned how to solve that. We're going to try and put 16 in base 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. I have to multiply 2 4 times to get to 16. Which obviously means that the x has to equal 4. 2 to what exponent gives me 16? 2 to the 4th exponent. So again, switching it from the log form to the exponential form makes it much more understandable. Okay, let's try another one. This one I'll give you as a multiple choice. This is from the final. It says find the value of log base 6 of 1 over 36. And here are the choices they're giving you. 6, 2, -2, and -6. Just as a hint, there are only 2 numbers here, and in a logarithmic expression, there always has to be 3 numbers. So they didn't give it what it's equal to. We don't know what it's equal to, so just call that x. In other words, yes?
No, I'm just saying good morning. I'm a little late, but I'm here.
Okay. See you now. I'm going to put you on the attendance. Okay. And I see Isis, you also came in. Isis, Jean, and Shania. Okay, and Ruth, and Jen, I see you just came in also.
Good morning.
Hi. Okay. If you have, pick one of the answers and put it on the chat for extra credit. Okay. We have Jean picked one answer. I'm gonna give extra credit. Jean, okay. And Oriana also gave me an answer, so she's getting extra credit. Okay, I think we should try and work this out and see which answer we like best. Hey, again, when I see something in logarithmic form, I'm gonna try and change it to the exponential form so it looks more familiar. So my base is gonna be the 6. My exponent, that's what we didn't know, so we're gonna call it x, equals 1 over 36. Now, what I could do is use each of these numbers in my calculator, if you know how to use your calculator for exponents. But I'm going to do it using just regular, my knowledge. Okay. Can the answer be A? What is 6 to the 6th power? Well, that's telling me I'd have to multiply 6 by itself 6 times. 6 times 6 times 6 times 6 times 6 times 6. That can't possibly give me 1 over 36. So that is not the right answer. A can't be the right answer. So let's try the next choice, 2. Can that work? Well, 6 to the 2 means 36. 6 times 6. It doesn't give us 1 over 36, it just gives us plain 36. But now I think, what makes it into a fraction? In order to get it into a fraction, in order to get it into the denominator, I need a negative sign. The difference, that's how we indicate a fraction with an exponent. So B is not the right choice, but 6 to the negative 2, which will mean 1 over 6 to the positive 2, which is 1 over 36, is the correct answer. The correct answer was choice C. Is there any question about that? Okay, let's see if we can do a couple more examples that have to do with logs and exponents. Here's a question from a previous final that looks like this. Log base 10 of x equals -4. And we want you to find out what x is. So is x 0.0001, 1000, 0.01, or -4? Which of these 4 answers is equal to x? I'm going to give you a few minutes to try that. And hint, try using your calculator with this. And I'm going to give you one more minute and then I'm going to work it out with you. Okay, let's do this together. Again, I'm going to take the logarithmic form and put it in the exponential form. What's our base? Our base is 10. The number on the other side of the equal sign is always our exponent. So this is 10 to the negative 4 equals x. Now, what does a negative 4 exponent mean? That means it's 1 over 10 to the 4th power, which means it's 1 over 10 times 10 times 10 times 10 is 10,000, which in decimal form is 0.0001. That's, so your answer is choice A. Of course, we could have done this with our calculators. Those of you who have a calculator, I suggest you try it now. We could have right away done 10 to the negative 4 in our calculator. 10, if you do this, put in the 10, press your exponent button, and then put in negative 4. Remember, not minus, the negative button, not the minus. So I'm doing exponent negative 4. And when I press it should give me 0.0001. So let me indicate something to you. You might have noticed on your calculator that there is a button that says LOG. Just a plain button that says LOG. So what is that button? How does it relate to what we're doing? Very often, when we talk about the log, where the base is 10, that is called a common logarithm. Log base 10 is called the common logarithm. And it's called the common, or it has a special name because the base that we're using for that number, for that logarithm, is 10, and our whole number system is based on the number 10. So very often, instead of writing log base 10 of x, you might see something written like this. Log 100 equals x. Or just say log 100. And what's interesting is there's no base written here. Now, remember I told you with logs you really need 2 numbers, 3 numbers. You need the base, you need the exponent, and you need the final answer. Log base b of a equals c. How is it possible that a log could be written without that base written in? it's not that it's forgotten, it means that what we're dealing with is the common logarithm, which means that really what we're talking about is log base 10. So anytime you see the word log and there's no subscript written, which means there's no base written in, it automatically means that the base is 10. It's like when we do a square root, a radical sign, and we don't put in the index, we understand the index is 2. Or if we write the word or the letter x, we know that the number, the coefficient, the number in front is 1, even though it's not there, it's understood. The same thing is true when you have a log. If a log is written without a base, it's what we call a common log, and therefore its base has to be 10. Now, if I do that, then I can solve this question, because my base is 10 and it's my exponent is x. That's what I'm looking for. I'm looking what the log is. That's equal to 100. And that's not so hard to figure out. 10 to what exponent is 100? 10 times 10 is 100. So the x has to equal 2. So that's something we should keep in mind. I'm just going to go do one more thing. Let's say I ask you to find a log of 1,000. And again, I don't write in what the base is. Now I could do it exactly this way because that's what we did, but there's another way you can do it. On your calculator, remember I told you there's a log button on your calculator? That button on the calculator is not just any old log. That is a common log. Anytime you have a question about a log where there's no base written in other words, that's a common log, you can probably use your calculator to figure it out because that button is a common log. So if you put in push the button log, and then you put in the 1,000, and you press enter, your answer is going to equal 3. And that makes sense because remember your base is 10. So that means 10, your exponent is that log, is 10 to the third is 1,000. So you can find common logs right on your calculator. Okay, I'm going to stop right here. And we're going to continue with our discussion of logs. We'll do at the beginning, as we've been doing at the beginning of each class, we'll do a quick review of examples from chapter 5. Again, if you have anything that you would like me specifically to review or spend more time on, either tell me in class or send me an email or a text or a chat, letting me know, can you review trigonometry? I'm just giving an example, and I'll make it a point at some point to review that topic. We'll be continuing, just as we are reviewing, we're still continuing with our discussion of new material. We have a little bit more to do on logarithms and exponents. I hope to finish by Friday the whole that, which will give us next Monday and Wednesday as total review days. But again, we are continuing our review and our new material. Does anybody have any questions they want to ask me? Okay, then have a good day, everybody, and I will see you Wednesday morning.